speaker is General Daniel Chibotero. I hope I pronounced that correctly. Chief Architect at Hailo Technologies. Uh, he's an award winner, laureate of the Israeli Defense Award for his work as an architect on a number of different projects working in the Israeli defense community. He's been a lead design engineer in the broadband access group at Broadcom, and worked on embedded software and chips for 10G PON there. So I'll turn the screen over to you. Go ahead.
So yeah, hi, I'm Daniel Chibotero. I'm the Chief Architect for Hailo, and today we'll discuss scalable, power-efficient architecture for deep learning at the edge. So I would like to start by saying that the Hailo A chip, our first product, is in mass production. It boasts the proprietary novel structure-driven data flow architecture. It has 26 TOPS, and it is able to process 1,223 FPS of ResNet 50 at 3 watts. In addition to our neural network core, it has also a vision subsystem and MCU subsystem, and multiple interfaces allowing realization of different system architectures and configurations. I would like to start by having a critical view at how Edge AI products are marketed. So basically, the headlines that you usually see is our chip has these kinds of TOPS, and our chips are power efficient at these TOPS per watt, and our chip is able to run this kind of FPS at the industry standard benchmarks, which is usually ResNet 50 or YOLO v3. And I would like to have a critical look at each and every metric. So basically, TOPS is the max deployed in the chip silicon multiplied by the frequency and multiplied by 2. And for most workloads, it cannot be utilized. The utilization of the max is usually influenced by the AI accelerator architecture and also by the neural network structure. And you can see here on the right 3 different AI chips, Edge AI chips, the Hailo 8, the NVIDIA Xavier NX, and the Mythic M1108. And you can see the difference of the max utilization for the ResNet 50 workload. And these numbers can, of course, change for different benchmark and different customer workloads. So TOPS is not a very good qualifier for, let's say, Edge AI product quality. The second one is the TOPS per watt, the efficiency metric, and it's not well defined across the industry. So sometimes it means the total TOPS in the chips divided by the chips TDP. Sometimes it is defined as the power measured for a synthetic workload that is toggling almost on the max on the chip, and it's very hard to gain insight on how this metric is defined. A better metric may be measuring max throughput and dissipated power, an ensemble of benchmarks, and obtaining the frame per second per watt for this ensemble, and then different solutions can be easily compared. In addition, for many customers, the pain point is not the power efficiency, it's making or meeting their product power budget, because it's a limiting factor for many products, because it is constrained by the passive cooling capability of the end product, it is constrained by the device junction temperature, and the requirements we usually get is, what FPS can I get for a given power budget, or does your chip power consumption scale down with FPS with regard to our benchmarks? The third metric that is usually out there is the ResNet 50 or YOLO v3 FPS. And we all know that ResNet 50 is already an outdated 5-year classifier, but I would like to have a look on what happened on the object detection field research field in the 3 years since YOLO v3 was published. So in 2018, YOLO v3 was the best object detector, edge object detector. And then in 2019, Efficient Det took the lead. And then in 2020, YOLO v5 took the lead. And usually customers make use of the most modern state-of-the-art networks and download the Git repository and start playing with it. And they would like the best achievable accuracy for edge, but they may settle for good enough accuracy if they gain throughput or they reduce the power consumption. So in our view, the Edge AI product is a triangle of trade-offs. You always trade off between the product's throughput, the product power consumption, and the product accuracy. And in the next slide, I will try to show how Hailo 8 meets different product trade-offs for some requirements we get from our customers. So the first product is a camera pole. The requirement there was a very accurate object detector with higher than 40 MAP accuracy on the COCO dataset. It should process 6 independent streams at real time, and the power budget is quite high, but it's again, it's capped at 5 watts for AI acceleration. And our solution or implementation on Hailo 8 for this product was running YOLO v5M at 191 FPS at 6040 by 6040 resolution. The quantized accuracy of our quantization algorithms is higher than 41 MAP, and the power consumption is lower than 4 watts. This is one example. Another is a video analytics solution, which required the person detection with quite low accuracy on a proprietary dataset, but it required 16 independent streams running at real time, and the power budget lower than 2 watts. So here the end customer took the MobileNet V1 SSD. Our benchmark figure for this network is more than 1,000 FPS and 2 watts, 300 by 300 resolution. But when measuring power consumption at the required frame rate, we go down to 1.2 watts, and it can be seen that the Hailo 8 power scales down almost linearly with the throughput. The third product is a mobile robot. It is connected to a single sensor at 60 FPS, and it should run concurrently semantic segmentation and object detection. Here we had also a latency requirement of less than 30 milliseconds from sensor to perception end, and also a power requirement of dissipating less than 3 watts. So in this case, we ran modified CenterNet ResNet 18 model for detection at 60 FPS, and ResNet 18 FCN16 at 60 FPS. The feature extractor were totally distinct, 2 distinct networks. And also, we implemented a system configuration connecting the sensor directly to the CSI interface of the Hailo 8 device. And this eliminates the need for a frame buffer and reduces the latency of the total system. And the power consumption here is at about 3.2 watts. So usually we are asked, okay, what can you give me at a 3 watt budget on Hailo 8? And one of the key strengths of our offering is the variety of networks allowing different trade-offs at the Edge AI product trade-off. So you can start with the YOLO v3 or CenterNet ResNet 50, both running at real time for a single sensor. And you can go up to YOLO v5 derivatives or CenterNet ResNet 18, which allows you to process multiple sensors at real time. And if you need, let's say, dozens of sensor processed, but at lower accuracy, you can deploy the MobileNet V1 SSD to Hailo 8 and get this processing power at 3 watts. Again, these are not the benchmark numbers, it's just what you can get for a specific power budget. Now I would like to highlight some of the advances we made in our software offering. The co-design of our hardware architecture and software allows the scalability and the power efficiency of the device across multiple workloads. And as a quick reminder, our architecture maps different layers in the network graph to the sea of resources, of hardware resources that is composed of control, memory, and compute in the silicon. And the software is in charge of doing it very efficiently and making use of the most hardware resources in the device. And the constant involvement of our software enables the mapping of newer models to the Hailo 8 seamlessly or almost seamlessly, and it constantly broadens the offering of power, accuracy, throughput trade-off for the end user. I just want to go through two quite recent features that were deployed in our software. The first one is in the domain of power efficiency. So for each resource that is not used during compile time, we set it in a power down or deep sleep, depending on the resource. But in addition, we are able to change the power state of the resource during runtime if this resource is used in an intermittent method. So this is one example for how our software enables a power efficient solution. The second is in the domain of scalability. And here we offer both control scalability and memory scalability, because one of the key drawbacks of data flow architecture is depletion of the resources that are already deployed in silicon. So let's have a look at control scalability. We have a possibility in our software to merge two different layers in the network graph to a single layer and then deploy it to, as can be seen here below, to a single control element in our hardware. And in this case, we are able to reach the control deadlock at a later phase. The second scalability offering is our memory scalability, where we can set layer activations or parameters or store them on the host memory and swiftly fetch them on demand by our NN core controller. And this, of course, happens seamlessly in our SDK or our software. So our current product offerings are the Hailo 8 chip, which can be deployed on boards, but we also offer M.2 models, the M key and the very size efficient 22 by 30 A plus E key. And we also have a mini PCIe module. And in addition, we also offer out-of-the-box examples that showcase the Hailo 8 processing capabilities of all these highlighted applications and the other running at real time or super real time on chip. So thank you very much, and hope to see you on the breakaway session.
Okay. Thank you, Daniel. wrapped up a little bit early, gives us more time for questions. So please go ahead and submit yours in the Q&A box. Um, the flexibility of your chip is impressive in a number of different neural networks that you've run. But we want to avoid the deceptive top spec as much as anybody. But you did say that 26 tops is the peak. I want to make sure I interpret that chart correctly. Are you saying 26 tops at 33% efficiency, or is that some theoretical maximum?
So again, everyone is quoting the number of tops, and it's basically the number of multipliers and accumulators that are deployed on chip. This is the industry standard. I can agree with it or disagree with it, but my point is that different workloads utilize these tops in different manner, and it's very dependent on the workload. And my example of ResNet 50 is only one example. Of course, we have other workloads that make use of the Silicon Max more efficiently, and other workloads that utilize the hardware less efficiently. But my point is that the discussion should be at TOPS utilization at certain workloads or certain points.
We totally agree. I just trying to understand how you derive the 26 tops.
I think that the way that everyone else does, just accumulating the number of multipliers and accumulators in the chip and multiplying by the frequency.
Okay, all right. And then what process technology are you using for Hailo 8?
It's 60 nanometers.
16, okay. Well, okay, so one of the questions from the audience was about the power. Your power that you quoted was just for your chip, not including a host processor?
Yeah, this is correct. Basically, usually our end customers choose their hosts based on their product requirements. And yes, the power efficiency quoted was only for the Hailo 8 chip.
Right, sure. But similar to some of the previous talks, you have a Cortex M CPU, I believe, on chip, and that once you start running the neural network, it runs standalone, correct?
Yeah, of course. The Cortex M CPU is used only for housekeeping of the chip or of the board and platform, and does not interact with the execution of the network on the Hailo 8 device.
Okay, yeah. It was good to see you using the accuracy in some of your comparisons. Some of our audience may not be familiar with the MAP, the mean average precision measurement. Could you talk a little bit more about that and how you measured that?
Okay, so basically the MAP is a used, let's say, the commonly used measurement to compare different detection networks. It's a very, let's say, it weights the misdetection and the false detection of detection networks. I won't go into the full technicalities of how it is done, but it integrates over the false detection versus misdetection of the network, and it gets a single number that is agreed in the machine learning community for the performance of object detection networks over agreed data sets, which is also very important. Sure,
right. And for the number of classes that particular application is using.
So the COCO data set, if I remember correctly, uses 81 or 91 classes. And this is it is harder to perform well on this data set than on other, let's say, older data sets, such as VOC,
Okay.
which has less classes.
Okay. And so I recall from the earlier analysis of your chip that we've done and published in microprocessor report, you have large on-chip memory. There is no DRAM interface, correct?
Yeah.
Right. So your approach is to handle the streaming data coming in from a camera, for example, directly rather than reading from a DRAM. Is there a potential bottleneck there? How do you?
Yeah, of course there is. This is why I also highlighted our possibility for memory scalability. So the easiest path is to, of course, concatenate multiple devices and then gain more memories. But we can, as I said, we can also connect through PCIe to the host DDR or DRAM. And in case we are reaching a memory bottleneck, we can offload activation, some of the activations, all the weights to the host.
Okay.
And then overcome this bottleneck.
Okay. And so it was interesting also some of the example applications you talked about from 6 camera streams to 16 camera streams. You have some sort of a camera interface ISP on chip, I believe. Is that correct? That handles.
Yeah, we have both camera serial interfaces and a vision subsystem which has an ISP on chip.
Okay. So 16 streams is a lot. I mean, is there a limitation on how many camera streams you believe the chip could handle?
So most of the system configuration I showcase are of an AI accelerator, which is attached to a host processor. And in many cases, the cameras are not directly attached to the Hailo device because due to cabling issues and the fact that many of the streams are encoded to be sent over the Ethernet. And then in many of the applications, we see the front end for the camera streams is the host processor and not the Hailo device. Of course, I've shown a single application where the Hailo device is the front end for the camera. But again, the vision capabilities of the Hailo device changes with the number of cameras and the input and the input throughput.
Mm-hmm, mm-hmm. Okay. You showed a variety of networks. Like I said from the beginning, a lot of flexibility, being able to go from ResNet to different versions of YOLO and MobileNet. Is there any particular type of architecture of a neural network you couldn't handle? I mean, your orientation is towards object recognition. You're not doing speech processing or those kinds of networks, correct?
So we are not trying to experiment with the device. We actually trying to keep up with the customer requirements for network architectures, and because we are vision centric, as we believe and our customers believe that the compute intense problems are in the vision domains. We mostly tackle vision-based architectures, and well, I won't disclose the architectures that we weren't able to map, but the vast majority of the architectures we encountered were mapped to the Hailo device.
Are your internal computations all integer 8?
The internal computations are int8. This is correct.
Okay. So, question on the input size for the robotics use case that you talked about.
Yeah, so it is proprietary data of our customers, but what I can say that the resolution is higher than HD for the network, and also the end customer supplied the specific models that match this resolution, but I think I disclosed the backbones and the network architectures for these two networks running on chip.
Okay. Question on using Halo 8 in an automotive application. I mean, your company really got its start with some of the funding coming from the autonomous vehicle development work in Israel. Are you looking again at automotive applications? Any ASIL requirements that you've addressed?
Yeah, so I didn't get into the automotive qualification of the Hailo device due to time constraints, but Hailo 8 targets ASIL B, the ACQ 100 grade 2, and as I said, our mass production of the commercial devices is has already started, and we are currently ramping up the automotive mass production.
Got it. Good. It was interesting to see. First of all, it's great to see you reporting on the true power consumption. You talked about it varying or even scaling linear with throughput, but it also seems to vary quite a bit depending on the type of neural network you're running. Could you talk some more about how you achieve that, your internal optimization and power management, and how do you do that? How do you adapt to different neural network models?
So again, it's a co-design of hardware and software. Of course, the silicon was designed a few years ago, but while designing the silicon, we had in mind how the software implementing each and every network architecture or kernel will be deployed on the device. And therefore, we were able to measure in pre-silicon, have estimations of measurements of in pre-silicon or of multiple networks, and in this case, make sure that our offering holds on a variety of network architectures. And there are a lot of details on how was that achieved, but basically the key for that is co-design of hardware and software in pre-silicon.
Got it. Okay.